Okay. All right, so let me reproduce that here. The spatial Eulerian acceleration, as we've seen, now is this. Okay, x fixed plus partial of v with respect to little x differentiated with respect to little t. Okay, and all of this is being done remembering now that little x is phi of capital X comma t. All right. Now, I'm going to do a couple of things here. That derivative, right, that partial derivative is simply the gradient, right? We're going to write it in that manner, okay? Where this symbol, nabla, is what we will use for any instance when we are taking the derivative, the spatial derivative of the derivative with respect to position of some function, but where the position here is the spatial one. Okay, so what we will label this as is the spatial gradient of v. But then what is partial of little x with respect to time, knowing that little x is just phi? Okay, so this term here is just partial of phi with respect to time. But what is partial of phi with respect to time? Phi is the motion after all, right? So its derivative with respect to time is simply the velocity, right? And we're going to write it as v of x comma time. Okay? So pulling this all together, and now I'm going to dispense with the explicit mention of the arguments little x and t, okay, just to keep this a little clean. So we have the partial time derivative of v plus gradient of v, the spatial gradient of v, okay, acting on the velocity v. Okay, all right. Everything on the right hand side is parameterized with respect to little x and t. So in fact, after saying that I wouldn't write it, let me actually write them explicitly so we can relate everything, we can relate the arguments to what we have on the left hand side. Okay, all right, and this is simply the same as the Lagrangian description of the acceleration, observing that there is a difference in terms of how we're parameterizing these objects. To probably round off our understanding of this, let me write it using coordinate notation. Okay, so with coordinate notation, okay, we would write A as A I E I, right, where what we're saying here is that A I is the partial time derivative of little v sub I plus partial of v I with respect to little x sub j vj. Okay? More here. When we write A equals partial of V with respect to time plus gradient of V, we recognize that what we have on the right hand side is indeed a time derivative. Okay? However, it's different from the partial time derivative, which is this, right? This is just the partial time derivative. Okay? This term is what sometimes gets called the convective time derivative. Convective because what we're accounting for is the fact that as this body deforms, particles are moving, right? They're moving with some velocity, but in doing so, they're also carrying along a certain amount of acceleration because each particle is moving, but then there are neighboring particles which are moving at different velocities, right? So when we want to parameterize the acceleration with respect to position of the particles only, the spatial current position of the particles, we need to account for the fact that there is a difference in the velocity between two particles, right, as they're tumbling through space. And that itself induces a further element of acceleration here. Okay, that's what we call the convective velocity. Convective because now we need to account for the fact that we need to convect with the motion to get all of the acceleration. Okay, and that's what the second term does for us here. The sum of the two is sometimes written as capital D of V with respect to time. This is called the total, or like I said, the material time derivative. Total because it's accounting not just for this immediate explicit dependence upon time, but also the fact that the spatial argument itself varies with time. Okay, so you're really picking up all of the variation with respect to time by doing this. Okay. And the best way to remember all of this is that this is simply now the derivative of V with respect to time. If you want to write it this way, you need to remember that what you're holding fixed is not little x, but capital X. Okay, they're all equivalent. Okay, just a matter of remembering what we are parameterizing things by. Okay. So as you can imagine, because of this property that we're really following the flow of the material and accounting for how the velocity differs between two neighboring particles, this type of description of the acceleration is relevant for fluid motion, right? Because when we're talking about fluid motion, you're looking at this little window here, right? You're parameterizing everything with respect to the position of this little window, right? And so when you want to write out the acceleration, you're accounting for the fact that if you were to look at this window or another window, there is going to be a difference in acceleration parameterized with the position of this window versus another window. And the way to account for all of that by following only the parameterization with respect to spatial position is to describe the acceleration as the Eulerian acceleration here. Okay? All right. If this is what we have, how can we apply this? Right? Can we apply this to what we just saw for rigid motion? It's fairly easy now. A for rigid body motion. Okay? Let's calculate this first. The partial time derivative of little v, okay, holding little x fixed. Okay. Recall that v of little x comma time for our rigid motion is simply c dot function of time plus q dot q transpose x minus c, okay, which is c dot function of time plus omega function of time x minus c function of time. Okay, so we'll take this in steps by first writing out the partial time derivative of v holding little x fixed. Okay, so partial of v with respect to time holding little x fixed. Okay, this is c double dot function of time plus omega dot function of time acting on x minus c function of time minus omega function of time c dot function of time. Okay? Now, there is another term we need to complete this expression for the spatial acceleration, which is this one, right? Looking back at our expression for v parameterized by spatial position and time, and recalling that this operator here is the spatial gradient, right? We observe that the gradient of v, the spatial gradient of v, is simply omega, which is a function of time, okay? And that acting on v just gives us omega acting on v, okay? So we're going to put all of these together, okay? And what we see now is that for our Eulerian acceleration, we have c double dot function of time plus omega dot function of time x minus c minus omega function of time c dot function of time plus omega v, okay, omega function of time v. Rearranging, we get c double dot function of time plus omega dot function of time acting on x minus c plus omega acting on v little x and t minus c dot function of time. But then we recall that v function of little x and time was originally written as x dot plus omega acting on x minus c, okay, which implies that here for v minus c dot we have omega acting on x minus c, okay. So we're going to take this and stick it in there, okay. And when we do that, we finally get back one form of what we had earlier when we explicitly wrote the inversion, okay. C double dot function of time plus omega dot acting on x minus c plus omega from there omega omega x minus c. Okay? And as the very last step, recalling that the skew symmetric tensors omega as well as omega hat can be written as cross products of the corresponding vectors, the corresponding so-called, by the way, those are called polar vectors anyway. So let me write this here. C double dot of time plus omega hat dot cross x minus c plus omega hat cross omega hat cross x minus c. Okay? Right? And this, if you compare with the expression we had derived in a previous segment, where we explicitly inverted the rigid body motion, you will observe that it's exactly the same. But now the nice thing is we did this without explicitly inverting the motion. Okay? All right. So we're going to stop here and pick up later.